So here we are given a tree, and then we are given a m subtrees, and we have the property that no matter what two subtrees you look at, they have a vertex in common. And then what we want to show is that there is a mutual vertex v in every single one. Trees are useful in graph theory because they have leaves, and they lend themselves very well to induction proofs, and that's what we're going to do today. We're going to proceed by induction, and the thing that we're going to look at is the number of vertices, so uh, the vertex set of T. Now, first off, we'll have this, the base case of the amount of vertices being 1, so just one vertex. Now, in this case, the only non-empty subtree is is T itself. So the one vertex in the graph will be mutual amongst all subtrees. Now next, for our induction hypothesis, I'll just write ind-hyp here. Assume that the property holds for up to n minus 1 vertices. And then consider some tree T with n vertices. Because our base case is 1, we know that the amount of vertices is going to be greater than or equal to 2. So this means may choose a leaf V. We know there's a leaf because it's a tree. And we let U be the unique neighbor of V. Now we are going to evaluate two different cases. In case 1, we are stating that there exists a tree Ti only with V, the leaf V. However, in this case, then, because we had in our original assumption that um, in the set of subtrees, all of them will have at least one vertex in common, pairwise with each other. So, because the assumption that this assumption here, we know that V must be in, we'll say, the vertex set of Tj for every j between 1 and m. So if there's a tree that only has one vertex, that vertex will be common amongst all of them because all of the other trees combined with Ti must have some sort of vertex in common. Then the more complicated case we can look at is case 2. And in this case, all trees within the subtree collection we'll just number that off T1 all the way up to Tm, have at least two vertices. Now, the most common thing to do in a induction proof with trees is to remove a leaf vertex, so that's what we're going to do. So we are going to define a new graph. We are going to let T prime equal T just without the leaf vertex, and additionally Ti prime, which is going to just equal Ti minus V for every I between 1 and m inclusive. So we can note that in this case, every ti prime must be a subtree of t prime because we're just removing the one vertex and we have now a smaller one. Uh, and we can also note that by our assumption, that should be a new sentence, by our assumption that all ti have more than two vertices, or more than one, can note every ti with v must also contain u, which is the unique neighbor. What this means is that uh, there is no two sets of subtrees uh, where the intersection is strictly v. So we can refer back here to our initial assumption that every subtree will have some vertex in common, but that vertex will not be v. We can recall that t prime is defined as the tree minus v, and that for the subtree ti, we have ti minus v. So what this implies is that, I should note that this here applies for every I and j between 1 and m, and that this ultimately implies that uh, the intersection of the any two trees in the subgraph T prime is also not going to be empty. Then we can note that given our induction hypothesis uh, right here, we can note that T has a vertex, T prime has a vertex in every Ti, so this vertex will also be in every Ti in this T prime plus V equals T. So that is all we needed to show, so we are done the proof.